We're talking about breadth first search on a graph data structure here. And I have an example graph on this side of my screen. And we're sort of posing the question to ourselves, is node A connected to node I? And how is node A connected to node I? And to do this, we're using breadth first search. And I want to look a little bit more at what these two data structures are going to hold, the frontier as well as this visited container. Now, our breadth first search, we want it to start at one node and then sort of expand out in all directions. So it's important to us the order in which nodes are added into this frontier because we want to get them back in the same order in which they were inserted. So remember, our frontier keeps track of the nodes that we still need to explore, and then the visited list keeps track of which nodes we have already explored, so we don't explore them again. Now, because our frontier, the order in which we add nodes into it matters, and we want to get them back in the same order, we want to make sure that we're using a data structure in here for our frontier that is a first in, first out, right? A FIFO. This is most commonly implemented using a queue data structure, right? So as we add elements in, we're going to get them back in the exact same order. Now, let's take a look at this question that we've posed for ourselves, A to I, and let's go through the example with this graph with the frontier and with the visited list. So we can see exactly what the frontier is doing for us and the visited list is doing for us. So to start this entire thing, to start our breadth first search algorithm, the first thing we want to do is look at our start node, A, and add that to our frontier and our visited. We want to explore out from that node. So we're going to take A and add it to the frontier and to the visited list. Now, when we are looping, when we're actually doing our algorithm, the question we want to ask ourselves to determine whether or not we need to stop or should stop is, are there still nodes that we need to explore? Breadth first search will explore the entire graph data structure. And we can ask ourselves that question of, in the way posing it as, are there still nodes here in our frontier? If our frontier is keeping track of which nodes we still need to explore, then it means we can ask ourselves, well, is the frontier empty? And if it's not, then we need to keep looping. We need to keep exploring nodes, right? So is the frontier empty? No. A is in here. So we need to explore A. It's the next node we need to remove from the frontier, and the next one we need to explore. So let's remove it from the frontier, or ask our frontier what the next node is, and it will tell us A. And now A is connected to E, B, D, and G. For each, as we're exploring a node, for each one of the nodes it is connected to, we're going to add it to both the frontier and the visited list as long as we haven't been there already, right? And which is what our visited list is for. So in this case, we're exploring A. We need to add E, B, D, and G. E, B, D, and G. And we add this to both our frontier and our visited list. E, B, D, and G. Is our frontier empty? Nope. Hey, frontier, what's the next node that we need to explore? Well, it's E, so let's remove it. Let's look at E. E is connected to F and A. F, we add to both our frontier and our visited. And then A, the other connection of E, already exists in our visited list, so we don't need to do anything with it. We've already been to A. We don't want to add it back into our frontier because we don't want to keep exploring back and forth between two nodes or keep exploring around this like circle or anything. So because we've already visited it, we don't add it back into our frontier. So in this case, when we explored E, we only added F because we've already visited A. Hey, frontier, are you empty? Nope, still data. So let's explore the next one, B. B is connected to A and C. A has already been visited. C has not. So we're going to add C to both of our data structures here. Hey, frontier, you empty? Nope, let's explore the next one. D. D is connected to A and C. A has already been visited. C has already been visited, so there's nothing for us to do here. Next is G. G is connected to F, A, and H. F has already been visited. A has already been visited. H has not been visited yet. It's new, so we need to add it to both data structures. Next, we're going to explore F. F is connected to E and G. E has been visited. G has been visited, so there's nothing for us to do here. Next, we explore C. C is connected to B and D. B has been visited. D has been visited. The next node we need to explore is H. H Now our frontier is empty, which is kind of interesting, but we're about to add something back into it. H is connected to G and I. G has been visited already. I has not, so we're going to add I into our data structures here. And then finally, we explore I. We remove I. I is not connected to anything, right? So, I mean, aside from H, which we've already added to our visits, so there's nothing for us to do here, right? Now, if we take a look, like this is when our algorithm would be complete. Our frontier is empty. There's no nodes left to explore. So we can do a couple interesting things here. The first is we can answer the question of, is A connected to I? We know it is because when we started at A, I was visited, which means that somehow we traversed from A to I. So answering the question of, is A connected to I at all? Well, it is, right? And in fact, we could modify our algorithm a tiny bit to say, well, as soon as we encounter I, as soon as we put it into our frontier or visited list, we can stop at that point. We know that A is connected to I. Now, the next interesting thing that we can ask ourselves is, how is A connected to I? To do that, we need one other data structure, right? This here is the guts of breadth first search using this frontier and using this visited list. And now it's sort of, we can use it and add some more flexibility to it and add additional data that we want to. So in the case of trying to answer the question of how is A connected to I, we want to generate a path that goes from A to I. We can do this by keeping track of which node did I add, which node was I exploring to add each of the previous nodes, right? So in this case, in this example, I just need to keep track of one other thing. I need to keep track of I was added to this data structure because of H, because I explored H, in which case I just need to keep track of I was added because I added H, or because I explored H. H was added because of G. G was added because of A. Right? And if we actually do this for all of our nodes, right? A added E, G, B, and D, right? B added C, so I can keep track of this. F was added because of E, right? And if you look at all these arrows that we could be generating as we're going through our data structure, we can actually generate paths from A to any other node. If you want to know the best way to go from F to A, well, it's F came from E, which came from A. Right? If you want to go from A to D, well, D came from A, right? A to C, C came from B, and B came from A, right? So adding this little bit of extra data gives us this power to generate paths. To do this inside code, what we would do is we keep track of one additional data structure. Whenever we add something to Frontier, whenever we add to the visited, we'd also keep track of this other data structure, which would be keeping track of, for this node, here's the node that it came from, right? So we keep track of like a dictionary or a map or something else along those lines where we say, I came from H, H came from G, right? In a very similar fashion, we could use this additional data using a breadth first search to answer other questions. You know, if each of the letters here were instead numbers, or these things had values connected to them, we could say, well, what's the sum of all of the values contained in this graph? Well, we could keep track of a sum, and as we're exploring and adding things to our visited, we could just continue adding to that sum, right? We could be keeping track of like what is the highest value, what is the letter that is furthest in the alphabet, which is connected to A. Well, let's start a breadth first search from A and keep track of the furthest letter from the beginning of the alphabet that we find as we traverse through this thing, right? So we just keep track of this other data as we're doing a breadth first search. The important thing to know is that breadth first search is this generic traversal algorithm. It uses a frontier and it uses a visited list. The frontier needs to be a first in, first out data structure. And then on top of this, we can layer additional logic to answer these questions. How do I go from A to I? What is the sum of everything, right? What is the biggest letter that's in here, right? We can answer these by adding additional data and additional logic on top of a breadth first search function. As a last note, one of the other interesting things that we can look at here is the order in which we traverse these nodes. Remember that with breadth first search, we want to explore going outward, right? And we're accomplishing this using our frontier. Well, if you take a look back at our nodes that were, as we were explored them, as they were added to our frontier, right? A was explored first, right? I'll note this over here in I don't know, an orange color. A was explored first, and then, or red color, and then E was explored. This was node 2. B was node 3. D was node 4. G was node 5, right? So we're sort of exploring outward from A. And then F, right? So exploring that way. And then C was 7. And then H was 8. And then I was node 9. So this is the order we explored these nodes, right? So started with A, and it traversed its way outward, right? It kind of like spiraled out from A, which is exactly what we want from a breadth first search.